All right, I hope everyone's ready for an adventure, because I sure am. Basically, I just want to touch base on the notes that I took for the first chapter of Agreste's easier categorical data analysis book, An Introduction to Categorical Data. Okay, so the key distributions for categorical data. Of course, binomial distribution. So assuming A, that trials are independent, and B, that the trials are identical, the number of successes in n trials will take on a binomial distribution with parameters n and pi. Okay, so as an example, 10 questions on a multiple choice test. There's 5 possible responses for each question. So if you take the test completely at random, the number of correct answers you'll get, y, will follow binomial distribution modeled by 10 choose y times 1/5, which is the probability of getting a question right, to the y times 4/5, probability of getting it wrong, to the 10 minus y. The expected value of y will be n times pi, or 10 times a fifth, which is equal to 2. So you would expect to get like a 20% on this test. And then the standard deviation is the square root of npq, which is about 1.265. Okay, it should be noted that as n goes to infinity, bn pi distribution will tend to approach normal distribution with its mean and standard deviation as stipulated here. Okay, the second key distribution is the multinomial. So you have the same assumptions, independent identical trials, but now there's more than 2 possible outcomes. Okay, so I have like a nice video on multinomial, but this is what it looks like. Now he points out that we don't actually use the density function, or in this case the probability mass function for this multinomial. So I'm hoping in later chapters it's explained why he shows it to us, but we're not going to really use it per se. But you want to know that the marginal distribution for each category of a multinomial distribution has a binomial distribution. Okay, likelihood function. Okay, basically what this thing does is it inputs all of the possible parameter values, and it outputs the probability of the data under those parameter values. So it's sort of this cursive L of, in the case of a binomial distribution, the parameter pi. So the maximum likelihood estimate, or the MLE, is just the value of the parameter that maximizes this likelihood function. So the MLE for a binomial, and when you're talking about this MLE, this maximum likelihood estimate, that's when you use this hat, okay? And it's always just going to be y over n, or the sample proportion. Okay, and P is a sample mean, which means that it has some nice properties of its sampling distribution. So the central limit theorem holds, and the law of large numbers. Central limit theorem is saying that for large samples, the distribution of P is going to be approximately normal. And the law of large numbers is telling us that for a large sample size, P itself is going to converge to the parameter value pi. What do I have here? Okay, before we get data, okay, this is just the difference between an estimator and an estimate. So before we have any data, the theoretical sample proportion that we have yet to take equals y over n is called an estimator, because it's basically like, it's like an operation for churning out an estimate. But once we plug in the data, we get the actual estimate of the parameter value. Okay. He shows us a significance test for binomial proportion. So the expected value of the proportion is equal to pi. The standard deviation of the proportion, or I guess you could say the standard deviation of the proportion is pi times 1 minus pi over n, all that square rooted. So to test P, I don't know why I have P parentheses P, under a null hypothesis of your choosing, for example, that P is equal to pi naught, you just use a simple Z statistic. So you take your, so the formula here is that Z is equal to the proportion minus the null proportion, the proportion, your estimate minus the null, divided by what's called the null standard error, which is just the variance computed as if the null parameter is true. And this thing should come from a standard normal distribution. And they give us a nice example. Okay, did the majority or minority of people say yes to abortion? And they surveyed 893 people and 400 said yes. So we simply form our sample proportion, 400 divided by 893, which is 0.4479. Subtract from that the null, divide by the null standard error, and we get the z-score of negative 3.11. How did I do this here? Right, I calculated like a p-value for this z statistic by saying like, look, what would be the chances of seeing a z-score this small or smaller, or, since we didn't specify one-sided, of seeing a z-score that large or greater, okay? And so it would just be twice the density that accumulates to the left of this value, because that would be the same as to the left plus to the right. Okay, so we calculate that that is about 0.002. So that's very unlikely. So it's fairly probable that we are not in a situation where we've got an even split. Based on our data, there's probably a majority or a minority rule. I don't like what I just said, but we're moving on. Okay. So inference then is all about tests of significance, which I just did like a pseudo test of significance. I did like half a test of significance because I didn't actually state a lot of the important variables that go into doing a hypothesis test. But tests of significance and confidence intervals. So how would you create a 95% confidence interval? Well, under our assumption that the sample proportion is going to be normally distributed, we can just take our estimate and we can come up with this null standard error, or actually in this case, this is using a standard error based on our proportion. Okay, times our critical z critical, and we can get this sort of a range right here. Note that we're using the standard error of the proportion rather than the null standard error. And I say for obvious reasons, but it's actually not so obvious to me. Okay, and then he shows us this, but then he goes on to say that this method is actually bad, especially if the proportion is near 0 or 1, and or if n isn't very large. So then he shows us that it's better to solve this equation for pi naught. So what's the purpose of this? Okay, well this will basically give us the sort of extreme possibilities of the proportion for which the z-score about our estimate would be 1.96. In other words, like a 95% interval of possible values of the parameter about our parameter. Or he came up with this thing, this is called the Agresti-Cool method, which is basically you just add 2 to each of the successes and failures. So you're going to be adding 4 to n total, and then you just use method 1 from there. And supposedly this gives you results that are very close to using this slightly more difficult method. Okay, and I guess I should mention, to actually solve this thing, you know, you've got to multiply by this, and then you've got to square. So you end up with like an equation that's quadratic in this pi naught. So then you have to sit there and solve that, and you know, you have to use the quadratic equation or some kind of you know, computer software. Anyway, okay, so then we get on to our big climax of the chapter, which is talking about these tests. So this is 3 ways of using the likelihood function, which we bothered to learn about already, to conduct inference. And what is conducting inference all about? It's confidence intervals and tests of significance. That's what inference is all about. But I believe we only will be talking about, we've kind of talked about confidence intervals all that we're going to. So I'm actually not sure how to use the likelihood function to do confidence intervals, but you know, we show how to do tests of significance. Okay, so the walled test. So this basically lets you test your parameter estimate against some null parameter. So it's very simply, we already sort of did this, parameter estimate minus null parameter over the standard error of the parameter estimate should be normally distributed. The walled statistic is the use of the standard error of the estimate evaluated at the estimate to calculate the test statistic. If you want to like say what a walled statistic is in a sentence, that's it. And walled testing is doing a hypothesis test using the walled statistic. Okay, I have this little note here, and I made a nice little video about it earlier, but chi-squared with k degrees of freedom means that you're summing up k squared standard normal distributions. Very good. Ooh, so I give a little example of a walled test. I think I have basically already done, actually, did I use, I'm just curious, in my last example, okay, so in my last example, I used the null to estimate the variance. So technically, this was not a walled test. This was a significance test under the null hypothesis. So make of that what you will. I still don't quite understand why you choose one rather than the other, but anyhow. Okay, so we're going to survey 100 people to see if they prefer dinner or dessert. 61 people respond that they like dessert more, and then what, 39 people say that they like dinner more. So is there evidence either way then that the true parameter in the population is not 0.5, and we'll say in either direction? Okay, well the MLE is the sample proportion, which is just 61 over 100, or 0.61. My null hypothesis is that pi, and we'll call it pi naught, is equal to 0.5. My alternative hypothesis is that it is not. Okay, I can go ahead and calculate the standard error of my parameter estimate. Well, maybe I should have a little hat on this, because even though it's the same thing, I've declared that this is the maximum likelihood estimate. Okay, so we just take our square root of p times 1 minus p over n, 0.0488. Okay, and then I do my subtraction, crunch through this, and I get 2.254. Okay, and we know that at the alpha equals 0.05 significance level, we reject H0 if our z-score is outside of the interval of negative 1.96 to 1.96, which it is. So we have strong evidence then that the population parameter is not 0.5. What do I have here? In walled test, you use the estimate of p to get its variance. Well, of course you do. That's my definition of the walled statistic. That's like what it is. Okay. Likelihood ratio. This thing's actually pretty cool. So the test statistic basically will automatically test the two-sided alternative hypothesis that, well, I could be explicit about it. I could say HA is that pi is not equal to 0.5. But in any case, here's how you run this thing. You take -2 log of, and all you do is you put in your log okay, so I should say what. Oh, no, this is just your likelihood function. We're going to log it in a second. You take your likelihood function evaluated at the MLE, and you take your likelihood function evaluated at your null. Okay? You take the ratio of them, and then you do -2 log of that ratio. And the idea is that this is going to have a chi-squared distribution where the degrees of freedom is basically equal to, it's usually going to be equal to 1 if there's just like one parameter that you're estimating. But suppose in your MLE you had like 5 parameters somehow, and in your null model, we'll call it, you had only 1 parameter. Well, then the degrees of freedom for this chi-squared distribution would be 4. Okay, and just to get like a sense of the intuition of this, we're talking about your likelihood. Now, suppose that suppose that the likelihood of the null hypothesis is much, much less. Okay, so you know that the likelihood of your MLE, let's say your likelihood function has something like this kind of shape, like, you know, either like a parabol, like an upside down parabola, or an upside down like normal distribution type shape. Now you know that the MLE is where the derivative of that thing is 0. Okay, and so that's going to have like the highest likelihood. That's the whole point of doing the MLE. So the likelihood of your null is going to be something less than that. Okay? Now, if it's close to it, like if this ratio is almost 1, like let's say your null is like just off of the MLE. Okay, this ratio is going to be close to 1. And what do we know about log? Basically, the closer you are to 1, the closer your input of log is to 1, as you approach, sorry, I'm being ridiculous here. Okay, as you approach 1 from the left, log approaches 0 from beneath. Okay? So if this ratio is getting close to 1, this thing is going to be sorry. Right. As your null is closer and closer to your MLE, this thing gets closer and closer to 1. Log of this thing gets closer and closer to 0, but it's coming at it from negative. So then if you multiply that by -2, you'll get like a small positive number, okay? And as we know from the chi-squared distribution, like small positive numbers have unspectacular p-values in a chi-squared distribution. Whereas let's pretend that this guy is very small compared to the MLE. If it has like, you know, if your MLE is up here, this thing is like down here, okay? Then this is going to be a very, very small number, okay? So let's say it was just more than 0. We know that log comes up. It's asymptotic with the y-axis as you approach 0 from the right. So if you just start coming off of 0 and you're moving to the left, that's going to give you a very, very large negative number. And when we multiply a large negative number by -2, we get a very large positive number, and as we know, in the chi-square distribution, large numbers have spectacularly small p-values. Okay, so that's the whole idea there. So if you are comparing models, oh yeah, I already said this. Okay, moving on. Okay, so the score test, there's not much I want to know about it, but there are a few things. Okay, we know that what the score function is you take your likelihood function, okay, you log your likelihood function, and then further you're going to take the first derivative with respect to your parameter. So you're looking at the slope of your log likelihood. Now, as we know, at the MLE, the derivative is 0. So when you're testing your sort of null parameter value, if this thing is far from the MLE, it's going to have, the farther it is from the MLE, the bigger its slope is going to be. Okay, and so I really am hazy on the exact details here, but basically to do the score test, you're going to take the score function evaluated at your null parameter squared, and you're going to divide that by the negative expected value of the second derivative of your log likelihood function. And somehow, magically, this thing is chi-squared. Okay, so as you could imagine, if this bad boy was really big, you know, if that slope to your log likelihood is very steep, the numerator here is going to be inflated, and then you're going to square that. So you would get some kind of large value, which is going to give you a spectacularly small p-value from your chi-squared distribution, which is going to indicate that there is something something funny going on. Right, if your maximum likelihood sorry, I don't know why I'm getting the giggles here. If your maximum likelihood is like really, really far from what you think the parameter is, then you know, there's good evidence that what you think the parameter is wrong. Okay, and so this is my quote from the text. In a score test, you estimate variance assuming the null hypothesis holds. Well, of course. I mean, what you plug in. Okay, I'm gonna leave it at that because honestly, I spent 4 hours today trying to come up with a concrete example for like a simple case, like, you know, like a binomial, like a 10 coin flips or something, to try to work through this, and I could never figure out how to get the expected value of what I was computing here. So if anyone watching this is like a statistics or math, you wouldn't even have to be a whiz. You would just have to be like moderately competent, I suspect. But if anyone knows the answer to that and they want to post it on my YouTube or email me at my Khan Academy website, which I think, no, just post it on YouTube if you're interested. Okay, thank you everybody. In the next installment of this brutal trying to get through this categorical data analysis course, we'll actually start with contingency tables and start working on actual categorical data analysis. Thank you.